All right, welcome to part 2 of the Rivers and Flooding lecture. So at the end of part 1, you contemplated drainage networks and came up with some definitions and rules for what defines a drainage or channel network. Here I've put down what some of my rules are. So a drainage network is going to be a network of streams and rivers, again defined by having those defined banks and a width and a depth. They're characterized by smaller streams that join together to become larger streams. There are many more smaller streams than there are larger streams. One of the interesting rules that I've noted is that the direction of the junction between tributary and main stem streams, so between these smaller streams and the larger streams that they become, tends to point in the direction of downstream. So what I mean by this is when you have two rivers that meet, they tend to meet and kind of form this Y form where the Y is pointing downstream. Right? So that's a major characteristic of kind of what we call quote unquote normal drainage networks. Drainage networks are also fractal in nature. So if we were to extend these smaller tributaries, they would be made of smaller tributaries. And those smaller tributaries would be made of smaller tributaries, which are made of even smaller and smaller and smaller. And so as you zoom in on the channel network, you get a repetition of the patterns and forms. So that's what I mean by they're fractal in nature. And then the other thing, which wasn't necessarily apparent from those pictures, are that drainage networks are going to drain to a base level. So the end of the drainage network is going to be some body of water, ultimately the ocean, which is kind of the global base level. But you may have some streams that drain into a lake, which forms a local base level. However, that lake, in most cases, eventually drains to the ocean. Exceptions to that are areas with internal drainage. Death Valley is one of those. A lot of areas in the Basin and Range part of Nevada are also internally drained, and so they don't actually go to the ocean. Right. A drainage basin is also more colloquially termed a watershed. So that's the area where all the water is going to drain to the same location. Right. We kind of implied that with our definitions of the drainage network, but just to make that more clear, every bit of precipitation that falls in that watershed should all drain to that same location, being in this example, the point that we drew. So a common example for the US is the Mississippi watershed. All water that falls as precipitation within the Mississippi watershed eventually goes to the Mississippi River. It may make its way through a couple other rivers first, but those rivers are all going to drain ultimately to the Mississippi. So this also means you can have watersheds within watersheds. So the Arkansas River is going to be a sub-watershed within the Mississippi watershed. All right, so now that we know how all of these streams connect, let's think about how all the properties of streams connect. And we'll do this through looking at longitudinal trends. So in this plot, we're going to be adding on these 5 different variables and looking at how they change with distance downstream, right? So starting from the headwaters, going down to base level. And we'll keep in mind that as we travel down a river, we have tributaries coming in. And so we're going to continually have more water being added as we travel down our stream. All right, so we'll first start with water depth. So as we travel downstream, the water depth is going to increase. And this might make sense. If you remember back in part 1, our images of kind of the mountain stream versus the lowland stream. The mountain stream was actually fairly shallow, whereas the lowland stream was pretty deep. So that shows us how the water depth is increasing. This is also going to have to be a natural continuation of the fact that we're adding more and more water as we move downstream because we have more and more tributaries adding water. We have more groundwater recharge, adding water to the surface water. Going along with the increase in channel depth is going to be an increase in the channel width. And again, that has to do with that accommodation of more water. there's just more things that need to be held in the channel. So the channel is going to get larger, both wider and deeper. What may be counterintuitive to this is that velocity increases downstream. So you may think that mountain channels, for instance, in part one, that mountain channel looked a lot faster than the downstream channel. But when we think about the drag forces, this makes a little bit more sense. The mountain channel had a lot of boulders in it. And so the water that was moving through was moving very chaotically. There was a lot of turbulence. Versus this high width and depth downstream channel doesn't have that much in it. And especially these lowland rivers tend to be fairly simple channels, not a lot of obstructions. And so the velocity can really pick up. So we get pretty high velocity with not as much turbulence. So what does this mean for discharge? Since discharge is velocity times width times depth, this means that discharge is going to increase a lot downstream. And again, this kind of confirms what we know, tributaries add water, so it makes sense that our volumetric flux of water is going to get larger as we go downstream. What this does imply, though, is that if erosion is proportional to discharge, that erosion would increase downstream, and that our downstream channels would just be so much more erosive than our upstream channels. And this may not be sustainable. Basically, we would have no stable ground down here by base level, by our oceans. So to counteract that, this nice geomorphic balance that landscapes do is that slope decreases downstream. So from our mountains down to our plains, we have lower and lower channel slopes, and this very nicely counteracts that increase in discharge so that the erosive power is kind of remains fairly steady throughout. And this results in what's called the graded river profile. So this graded profile is the exact balance of the erosion from discharge and slope that makes an equilibrium channel. So what we're looking at in this is called a longitudinal profile. And we're simply looking at a side view of the river, starting with its elevation up at the headwaters and looking at its elevation as we go downstream all the way down to base level. So for rivers like the Arkansas, this would be, the Rocky Mountains would be over here. We get into Colorado Springs kind of at the transition to the plains, to the Gulf of Mexico, eventually through the Mississippi. And at each point in the channel, and wherever you are within this graded channel, the slope and the discharge have been perfectly balanced in order to transport and erode the size of rock that's there. So when I said earlier that we're balancing erosion, it doesn't mean that no erosion is occurring, but it's balanced so that erosion is occurring on exactly what is present in the channel. And so that kind of leaves the question, what is present in the channel? We tend to have boulders, cobbles, and then we get down to sands and silts in the channel. So when we're thinking about this balanced erosion, there is actually more erosion potential closer to, the headwaters, the Rocky Mountains, because the river has to move things that are boulder sized versus closer to the Gulf of Mexico and base level, the river is moving things that are silt sized, so much, much smaller. And so that erosion is going to be a little bit lower. So that is one thing to think about with hazards. Even though the kind of amount of erosion is going to be similar, the things that are being eroded are very different, and that may affect what the hazard is to you as the person, to your property, or to your house. All right, so if we're perfectly graded and perfectly balanced, why on earth do we get flooding? That kind of doesn't fit with our perfect balance situation. So what's up with flooding? Flooding is going to be a product of that magnitude frequency balance, which we mentioned earlier. So the riverbanks, for example, these ones here outlined in red, are formed during the peak of the magnitude frequency curve for river flow. And this is actually a flow level that's called bank full flow because it's the flow level that has created the banks and for which the banks are defined. So at bank full level, the water would be all the way up to the top of these banks. This occurs about once every 2 years. So that 2 years, that's the frequency level that perfectly balances with magnitude to create the channel form. When this is exceeded, we tend to get flow that overtops the banks and floods. So things greater than a 2-year flow tend to be flood events. Things lower than a 2-year flow tend to just be normal events that are kept within the river. So in order to understand what that 2-year flow is, we could just look at the banks, but that doesn't actually give us discharge because we're missing the component of velocity. So what we have done is use gauging stations. And in your labs, you've probably learned a lot more about gauging stations. So I'm not going to go over those in too much detail. But these allow us to record the river discharge continuously. They often operate on a 15-minute time frame, and they've been in operation at hundreds of sites across the United States for 100 years, or in some cases a little bit less. But this allows us basically to know what river discharge is and how often it has occurred. So this gives us the magnitude, and then the recording through time gives us the frequency, and we can see how these balance out, right? So this plot on the bottom is a fairly typical one. We see the flow rate, so the discharge, which is the magnitude. And then we see percentage exceedance. And this is a way of looking at frequency by saying, statistically, how often are we likely to see a flow greater than a certain size? So a 2-year bank full flow, if it occurs every 2 years, in a single year, you have a 50% chance of it occurring, right? So an easy way to calculate that is this is called the recurrence interval when we talk about it in the form of years. And you just do 1 over the recurrence interval to get at the percentage exceedance, right? So 1 over 2 is 0.5, and that's 50% exceedance. And so that's exactly where these blue arrows are pointing to in the diagram. So we can use this diagram to pinpoint what flow occurs every 2 years or 50% exceedance. We can then go over to the flow rate, and that tells us that for this particular system at 1.6 cubic meters per second, that is the flow that has defined our channel banks. And any flow greater than that will be a flood. Any flow less than that will just be normal. You don't have to worry about it. So this is how, for the most part, across the US, we define what flood risk is and what the flood hazard is. There are a few potential problems. So for one example, this image here shows a 300-year flood in the Chehalis River. This is in Southwest Washington State. And this is actually where I grew up. So this kind of helped me get into geomorphology. But one of the interesting things about this that points out some flaws in our thinking is we only have 80 years of a stream gauging record. Europeans, white European settlers did not come to this area until the 1870s, and we definitely didn't install stream gauging equipment until much later than that. So we don't actually have 300 years to reference this flood event. And so we are, taking this record here, and we are way extrapolating it, right? We're drawing this curve way up here in order to say that this is a 300-year event. And we don't know that this direction of the curve stays linear for this amount of time. So this is some flaw when we talk about flood risk is we don't really have enough information to capture these high magnitude, low frequency events yet. This event may end up, after a longer record, we may note that it's actually a 100-year flood event. And so we would expect it to occur much more frequently than we initially thought with this limited data set. The other thing that comes with flood risk is we want to balance the gains from floods. Floods are a natural process. And as such, the landscape is kind of adjusted to having flooding. Floodwaters tend to deposit a lot of silt and clays with them when they top the banks. Since the flow is not channelized, it tends to kind of just, anything that's in the flow that's being transported in it kind of just settles out and falls onto the ground. And those silts and clays tend to have a high nutrient value. Because clays have a charge to them, they can actually carry a lot of ionic nutrients with them that larger grain sizes can't do. So there's a lot of value to floodwaters in terms of replenishing ecosystems and for ourselves for replenishing nutrients in farmlands. Right, so this is an example from Snoqualmie River where everything this image is at a bankful stage, and all of the fields around it really benefit from having floods. And this is actually an area where we let it flood. We've decided the benefits are great enough, and for the most part, houses are out of the way. But this does create the problem where we have to balance the risk of flood to infrastructure and to ourselves with the economic value that flooding can bring. So we have kind of some imperfect solutions there, and this is something that would need to be worked on in the future, and that we need geoscientists to continue to think about. Right? So we have things like flood walls, where those can fail. We have levees, those can burst, as we may all remember from Katrina. We have dams, which can control and regulate floodwaters. However, those have negative effects in terms of interrupting in-stream habitat for fish and turtles and other species, as well as for interrupting the cycles by which trees and other plants are trying to spread pollen. It's also going to trap a lot of those high nutrient sediments behind those dams. So we have some problems, we have some solutions that need to be figured out. All right, so once the water has made it through these lowland rivers, and maybe it's flooded, it's come back into the river, we end our journey at deltas. And I really like the symmetry of this, that deltas kind of mirror the tributaries that we see in the mountainous areas through what are called distributaries. So instead of all of the smaller channels joining together to create larger channels, we have larger channels splitting or bifurcating to form smaller channels in a very nice parallel. I mean, you can see some really cool examples of that below. The one on the right is the Nile River, and you can see immediately from satellite photos exactly how valuable this river was for agriculture and for just creating an environment where civilization could blossom and flourish. And we have other deltas, this one from Alaska, and I don't remember where the one on the right is. And then we also see deltas in other planets. So really cool thing that's happening in the middle of our block actually is that the Perseverance rover is landing on Mars with a planned date of February 18th, 2021. And Percy, call him Percy, is landing in Jezero crater, which is this crater right here. And one of the reasons this landing spot was chosen is because it's in the middle of this feature that really resembles a delta. You can see you've got a main channel that branches off and continues branching. So this very similar distributary form. It creates a fan-shaped form that's really similar to the deltas we see on Earth. And could be some really cool evidence of long-lasting water on Mars. So that's very exciting to think about. All right, so this ends our trip through the water cycle. We started with precipitation in part 1, and in part 2, we thought a lot about rivers and how different properties change along rivers to lead to different erosion and flooding hazards. And then we kind of very briefly ended at deltas. So now that you've finished that, don't forget to go back to your conceptual diagram where you drew what you thought the water pathways were and annotated hazards along the pathway. And I'd like you to go back and rethink this diagram, make any adjustments you have to do, note anything that really kind of surprised you or changed in your conceptual thinking about flooding in rivers. Don't erase your first diagram. You'll be turning these in as homework, and I love to see that progression in your thinking. All right, so that's the end of part 2 of flooding and rivers.